where we are right now, where we finished in the previous class. You remember, so we played with eigenvector equation, right? We wrote for for the eigenvector k and for the eigenvector L, we massaged one of those, combined them, and we ended up with this equation, right? So lambda k minus lambda L. Okay, so we ended up with this lambda, again, forget k minus lambda L, lambda k minus lambda L, and then we had a k transposed T A L equals to 0, right? So we ended up with this equation. And in the previous class, we pretty much spent the whole class analyzing one special situation where or when eigenvalues are different. All eigenvalues of the system are different. So basically all frequencies of normal modes are different. In that case, if they are different, then this factor, of course, cannot be 0. And then in order to make this correct, in order to make it 0, this part must be 0. And that is automatically, it tells us that our eigenvectors are automatically orthogonal to each other, which is great. So because we want to use these eigenvectors eventually as the basis for our general solution, right? So we discussed it, we played with that, and then now the second situation. What if we have degeneracy? Degeneracy, it means that you have, if you take, okay, not, let's say, if you have two different normal modes, they have two different eigenvectors, but their eigenvalues are the same. It happens, right? Things happen, right? Things happens. So in that case, if there's a degeneracy, we're going to look at only the sort of easiest level of degeneracy when we have only two eigenvalues are the same, right? So if lambda k equals to lambda L, then this is 0. And this, just this guarantees that this equation will be correct. And then as a result, we cannot say for sure anything about this part of this expression, right? Maybe by accident, this can be also 0, but again, no one can guarantee that. Because this is 0, and immediately that satisfies this equation. This equation will be correct. So in this case, AK and AL are not automatically orthogonal to each other. Again, it's possible by accident, but again, we cannot trust. We cannot trust that, right? Chances can be minuscule, right? Okay, as a result, but it's not the end of the life, right? Since we know a well-known procedure, Gram-Schmidt procedure, which can be used to orthogonalize any elements, as long as you define what do you mean by if you define what you mean by orthogonal, then you can orthogonalize any elements. So for example, you can have n some functions, right? And if you define what do you mean by orthogonal, and according to that definition, all those functions are not orthogonal to each other, using this procedure, you can create a new set of functions and they will be orthogonal to each other. And we looked at the simplest possible situation at two-dimensional vectors at the end of the previous class, just to demonstrate what's the idea, what's the logic behind a Gram-Schmidt procedure. It's good to have first clear logic, clear idea. Right, okay, so that's where we finished the previous class, and now let's apply Gram-Schmidt procedure for our particular situation, right? But yeah, probably let me write first. You know what? No, let me write what I wrote at the end of the previous class, because it logically makes sense again. All right, so now, right, so when k is not equals to L, different normal modes, but eigenvalues are the same. Lambda k equals to lambda L, so we have degeneracy. Degeneracy, right? And as I wrote at the end of the previous class, in this case, lambda k. Okay, AK is not perpendicular to AL automatically, right? Okay, so now Gram-Schmidt procedure. Let's apply. So let's apply Gram. Okay, now I'm afraid of misspelling. No, correct. Schmidt procedure. Right. Okay, so let's assume that we solve our eigenvector problem, right? We found all the eigenvalues and eigenvectors, right? And so let's assume, right, let me put here a new bullet. So now let's assume that we got two eigenvectors, a k prime and a l prime, and they are not orthogonal to each other. Eigenvectors are not orthogonal to each other, of course. So I'll skip to each other, not orthogonal. And because, so, and of course, the corresponding eigenvalues, let's say this has the eigenvalue lambda L, and this has lambda K, which is equal to lambda L degeneracy, right? And basically, because of this fact, we cannot say that they are orthogonal. Okay, so that's basically initial situation, but we're going to impose two additional, not the facts, statements. Once you get eigenvectors, of course, you can normalize this. Normalization procedure was introduced, right? So let's assume that we normalize them. It's not completely necessary, but nice. We can do it anytime, so it's not a big deal. So we can make that assumption as well. Right. Also, assume they are normalized. So basically, it means that a k prime transposed t a k prime equals to 1. And it makes you understand why I'm using primes. So here I didn't use primes, and here now I use primes, because these are not our final results, right? So these are right now sort of like a preliminary results, and at the end we will get vectors ak and al, a sub l, right? So that's why primes was introduced, right? And the second, and al transpose prime t a sub l equals to 1. Okay, so normalization is also assumed. So this is initial state. And now we need to create a new set, in this case, two eigenvectors, but now but now they should be orthogonal to each other, right? So now let me write. So let's construct two new vectors, eigenvectors. I should emphasize, eigenvectors. So new vectors cannot be just any arbitrary vectors, right, orthogonal to each other. No, they still must be eigenvectors. And moreover, they must have exactly the same eigenvalues. Because we cannot change eigenvalues. System is given. And if system is given, so frequencies of normal modes are predetermined by the God, right, who created the system, right? So we cannot change the frequency of this system. So eigenvalues are given. But of course, we can use different eigenvectors. We can come up with different There we have some freedom. So basically, that's what we use here. We use that freedom that we can use, can come up with different eigenvectors, but eigenvalues we cannot change. Two new eigenvectors, right, which are orthogonal, of course. Which are orthogonal. Okay, so, and then remember the procedure which we described in the at the end of the previous class. First, you can take any of the vectors and keep it, and then relative to that vector, you will introduce the second vector, which is going to be orthogonal. So let's keep a k prime, and then we will construct al instead of al prime, right? So let's keep a k prime. And then let's construct. Right. And then second bullet, construct a sub L, which will be, okay, what can we do? The simplest operation which we can use, pretty much linear superposition of these two vectors, right? Why not? Let's try it. C1, as long as it gives us what we want. Right. So the simplest, let's just construct a linear superposition, right? So it will be C1 A K prime plus C2 A L prime. Okay. And so now basically we just need to find these constants. We need to properly choose the constant C1 and C2. But before we start finding C1 and C2, what do we have to check? Just to be safe, Again, you remember we want to get not just to any vectors, we need to get eigenvectors. And with this eigenvalue lambda L, right? So let's quickly, before we start finding these constants, let's convince ourselves that this new vector AL is an eigenvector with this eigenvalue, lambda L. So let's do it. Right. Okay, so let me write. So let's show that AL is an eigenvector with eigenvalue lambda L. It's very important. Okay, so do you remember eigenvector equation? We used it already so many times, right? So it's a V A sub L. Okay, since we are testing this, must be equal to lambda L T A L, right? Yeah. Okay. So if AL satisfies that, then yeah, it's an eigenvector with an eigenvalue lambda L. So it's an eigenvector equation. Let me again emphasize. So it's an eigenvector equation. Okay, so let's start from this side. V A sub L, it will be V and our construction plus C2 A L prime. Okay, so it's a procedure you see quite straightforward, and it's more or less obvious that it's an eigenvector. Right, so C1 constant, C2 constant, of course we can take them outside, so it will be C1 V acts on AK prime plus, okay, I'll try to squeeze C2 V acts on AL prime. Okay, V AK prime, we know that both of these vectors are eigenvectors, so they satisfy. Okay, let me frame this because it's sort of, right, we need it. So we know that the eigenvectors, it means that they satisfy this equation. So V acting on AK prime should give us lambda L, okay, lambda K, but lambda K equals to lambda L, right? So this is equal to lambda L T A K prime, right? And this also Al prime also is an eigenvector with this eigenvalue, so it must satisfy this equation, eigenvector equation. So this is equal to lambda L T A L prime. Okay, so now we have a bunch of constants. We can take them outside, and T is the same for both of these terms. Of course, we can take them all out, the same eigenvalue, because we have degeneracy. So it will be lambda L T, and inside we'll have a nice construction, which is our newly introduced vector AK prime plus C2 times AL prime. Okay, so this is A sub L. So we're getting lambda L T A sub L. Yes, A sub L satisfies this equation, eigenvector equation, so it means that A sub L is an eigenvector with this eigenvalue. So great, it will work. It will it satisfies the criteria, right? In order to even to be qualified, right? So it passed the qualification, and now yeah, we need to write the equations for C1 and C2, right? Okay, and so basically this is sort of like a preliminary steps, and now actually let's get constant C1 and C2. So now small bullet, and now C1 and C2. How can we find these constants? And of course they should come from normalization procedure, right? That AK prime and AL orthogonal to each other. And the second equation, because yeah, it's good to have a set of orthogonal vectors, but it's even better to have a set of orthonormal vectors, right? It's like in Cartesian coordinate system, x hat, y hat, and z hat. They are not just orthogonal to each other, they orthonormal, right? So they also normalize. So the second equation will be normalization. We're going to normalize of course, vector A sub L, because A sub A prime, A sub K prime is normalized already. Right. So those two equations, orthogonalization and normalization. So let's start with conditions for these two vectors be orthogonal to each other, and it's this basically, right? But of course for our vectors. So okay, maybe right. Let me write orthogonalization. Difficult to write. Okay, let me try to write at least one line. So it will be AK prime transposed, right? T A L, and actually, you know what? Let me follow my notes. I used L first here, and then AK prime, the last one. It's not a big deal, right? So it just feels safer if I follow my notes than if I made some mistake. Then it will be probably easier to find where I made a boo-boo, right? L K prime. Right. Okay, and it must be equal to 0. But of course, equals to 0 I will write at the end. So now let me write explicitly, instead of AL, you know what? I feel like framing this as well, right? Because I will need it from time to time. It will be easier for me to find it. So it will be, so, transposed, C1 AK prime transposed plus C2 AL prime transposed T and AK prime, and it must be equal to 0, right? Okay, now I need to move to that side. We just need to open the brackets, right? It's trivial. So now, okay, let me put this arrow, and it will be C1 A K transpose prime times T and A K prime, and then plus C2 A L prime transposed T A prime. Okay, so now obviously this is normalization, which we assumed from the very beginning, right? Which can be easily done again from the very beginning. So this is just one, and yeah, that is needs to be calculated. It depends on the problem, right? If the problem is given, matrix T, basically you can extract, and then we assume that AK prime and AL prime you found, right? So that's the initial condition, right? So basically these can be calculated. So, and it must be equal to 0 because it's the normalization, orthogonalization, right? So from here we can get immediately, probably I will just write ratio of C1 over C2. Let me write it like this. C1 over C2 equals to minus AL prime transposed T A K prime. So that's the equation number 1. I can put number 1. Again, equations for C1 and C2. And now the second equation, because yeah, we need the second equation, can be the second equation. In order to get the second equation, we can use, as I said, normalization of newly born, newly introduced vector A sub L. Right. Okay, so now normalization of A sub L. Okay, normalization, it's basically this, but now for A sub L. So it will be A sub L transposed T A sub L. It must be equal to 1. Okay, now it's a little bit messy, but not that bad. So now let me write explicitly. Okay, here I have to be careful. All right, so it will be C1 AK prime transposed plus C2 A L prime transposed, then T, and exactly the same but without transposition, AK prime plus C2 AL prime, and it must be equal to 1. Okay, so now we just need to carefully, first I will probably get quadratic terms, so basically AL and this with that, and then this with this term. Right. So let me take care of those two terms. So will give me, it will give me C1 squared, this and that term, right? First I'm combining this with that. Then AK prime transposed T AK prime. And immediately what is that? AK prime T AK prime. Okay, transposed. It's a normalization of the vector AK prime. So that is equal to 1 immediately, right? Right. Again, it's not a unit matrix, it's just a 1. Right. Then this with that. It will be exactly the same, but now with AL prime. Okay, let me write it down. So it will be C2 squared and AL prime transposed T AL prime. And again, this is just 1. And then sort of like a cross terms. Cross terms, it will be this with that, and then that with that. So let me start with this outside, guys. So it will be C1, C2, AK prime transposed, TAL prime. And then this inner terms, this with that. So it will be the same, but now AL prime transposed and AK prime. C1, C2, and AL prime transposed, T, A, yeah, AK prime. AK prime. And it must be equal to 1. Okay, let me write. Basically, I want to show now that this term and that terms are identical. In order to do it, let me write them in a component form. Very often, in order to see what is inside, yeah, it's better to write it in a component form. It's messier, but more informative sometimes. Right? You know what? Let me use blue. So let me write it over here. So it will be, let me start from the last one, A prime LJ, then TIJ and A. Okay, strictly speaking, now it should be KI and transposition on top. But let me apply transposition immediately and flip indices. So instead of KI, I will write IK. Right. So IK. So transposition is already applied. Okay, so that's what we have here. Now, what about this guy? This term. Okay, this factor. Again, let me write in a, okay, you know what, let me separate them so that they wouldn't overlap. And so exactly the same. Transposition I apply immediately, so it will be A I L prime, T I J, and A J K prime in a component form. Then, now, oh look, you remember our matrices V and T are symmetric, real and symmetric. So Tij, of course, is equal to, okay, let me use different. So Tij, where should I write it? Okay, maybe underneath. So equals to Ji. And now, after this flipping indices under T, since all these indices are dummy, they don't go outside of this term, right? Outside of here, the summation, of course, they don't go outside. So we can change the indices, right? So we can, for example, change I and J, interchange. We can call I as J and J as I. Okay, basically I as J is enough. I as J, right? So as a result, this will be equal. Okay, let me write underneath. It will be the first A J L prime T J I, and then since we're flipping, so it will be I J T I J T I J and A I K prime. Now let's look at this carefully. Hold it, too many primes. Oh no, it's correct, it's correct. Here prime is missing because now I started comparing, okay, this prime. There must be a prime over there, right? Because now I started comparing these two terms and where the prime. Okay, look. AIK prime here, TIJ here, and AJL here, exactly the same. Of course, in order to get the right form, of course, this must be moved to the first term, to the first place, and this must be moved to the last place in order to sort of go back to the matrix form. So now I can write, so they are the same. Right. Okay, cool. It means that this term and that terms are the same, so we can write only one of them. Okay, so now let me, after this I have to rewrite, so this will be just c1 squared, c1 squared plus c2 squared, and plus, which one I used? Let me look at my notes, which term I actually decided to keep at al prime. This one, the last one. Okay, whatever. So it will be a plus 2 c1 c2 and al prime t a wait t a k prime, and it is equal to 1. Equation number 2. Again, this can be calculated because, again, from the very beginning, we assume that we know these vectors, eigenvectors. We solved the problem, we found those eigenvectors. Again, since you have a problem, you wrote down the kinetic energy matrix, potential energy matrix, so T is given, so you can calculate this. So it will be something, right? Some number. And then, so now we have this equation and that equation. Two equations, two unknowns can be solved. Okay, so let me frame it. So equation number 2, right? 1 and 2 can be solved for C1 and C2. So 1 and 2 can be solved for C1, C2, right? Okay. That's the procedure, the end. And of course, we looked only at the simplest possible situation when we have sort of degeneracy of the second order. If you have 3 eigenvectors belonging to 3 different different normal modes, and 3 eigenvalues are the same, then idea is exactly the same, but complexity increases tremendously, right? It's usually for the first couple of years I tried to go through that. In general, it's messy, right? So, and then I decided, no, it's not worth of troubles. So the lowest level of degeneracy, considering only this, is enough, I think. So that's how you can handle a case when there's a degeneracy and you cannot guarantee that your eigenvectors are orthogonal to each other. So you can, in that case, you have to digress a little bit, adjust your eigenvectors and introduce, instead of these guys, 2 new eigenvectors. And again, they're still eigenvectors with the same eigenvalues, because I emphasize eigenvalues we cannot change. Again, they're eigenvalues, basically frequencies of the system, right? Frequencies of normal modes. It's beyond of our reach, system is there, so it's all predetermined. Right? But which basis to use to write down the general solution? Yeah, we have some freedom in that. Right. Okay, so now, so after this, basically, we can write general solution. Now it's time. Because why we didn't write it earlier? Since we want to, we needed to guarantee that all our eigenvectors are orthogonal to each other, right? So only then we can construct a linear combination of them. Right. So now, since we know how to handle even a degeneracy situation, now we can write general solution. Okay, I will write. So now, general solution. Finally. So probably first, let me remind you in which form, solution in which form we were trying to find, right? So it was, which subscript I use? Okay, let's use K. Eta K equals to Ck amplitudes, right? So a column of amplitudes, AK, and the time dependence e to the power of minus I omega t. So that was our candidate for a solution. in a complex form. Of course, you'll have to, at some point, you have to take the real part. Right. Actually, now we can, okay, I will add it in a second. Ck is a complex constant, right? So let's reveal its complexity. And of course, you remember any complex number can be written as an amplitude times exponential e to the power of, right? So Ck complex, so let me write it like this, f sub k and e to the power of minus I delta, right? Again, any complex number, you can write it like this. It's not a big deal, right? You know that. And so now we can write a solution for the one of the normal modes. Again, it's not a general solution. It's just a solution which describes motion of one of the motion of all particles. Let's say it in this way: motion of all particles in the case normal mode, right? So K mode, right? In a complex form. First, let's write in a complex form. Complex form. So it will be okay. First with ck, right? Then column of amplitudes A1k, A2k, and so on, ANK. Again, you remember, first index tells us which particle. It's the amplitude of the first particle, amplitude of the second particle, amplitude of the nth particle, and the second index tells us which mode. So amplitude of the first particle in the case mode, second particle in the case mode, and so on. Right, and then, okay, first, okay, let me write like this. So minus I omega kt, and of course we can write now using this explicitly, right? So it will be fk column of, too narrow, column of amplitudes a1k and all the way to ank, and e to the power of minus I omega kt plus delta. Okay, let me rewrite it. I just need to move it to the left slightly to get myself a little bit of space. All right, so minus I omega kt plus delta k. Okay, now I could fit it. Of course, minus in front. Still in a complex form, right? And of course, we need to take a real part because these are displacements of an actual particles, and of course displacements from the equilibrium cannot be some complex. No, these are real, right? So real part. And again, it's not a general solution for now. It's just a case mode, normal mode, right? So the real part, of course, still K mode will be, okay, now real part, Fk column of amplitudes, Nk, and cosine of omega kt minus delta k, right? So let me, yeah, of course. Again, it's still kth mode. Okay, so now, as I said, since all these eigenvectors are orthogonal to each other, plus normalized, right, to make our life a little bit easier, a little bit better, right? So now, linear combination of all these modes is the general solution of the system. All right, I can erase all this. Okay, probably let me again write finally general solution. So that's the sort of title of the section. And now actually we're ready to write a general solution. General. Okay. Again, general solution give us displacements of all particles from the equilibrium. So we need to write a column of displacements eta 1, eta 2, and so on, all the way to eta n. Again, eta's displacements from the equilibrium, you remember. First particle, second, and so on. And now linear combination, right? F1 column A 1, 1. It's a amplitude of the first particle in the first normal mode, then amplitude of the second particle in the first normal mode, and then all the way to amplitude of the particle n in the first normal mode. And then time dependence, cosine of omega 1 t minus delta 1. Then plus F2. Okay, let me write also the second. So it will be the same, but except for the column, or I mean the second index will be 2, right? Amplitude of the first particle in the second normal mode, amplitude of the second particle in the second mode, and amplitude of the nth particle in the second mode. And time dependence cosine omega 2t minus delta 2 plus, and so on, plus and let me write the last term. So it will be Fn, column of amplitudes, 1n, amplitude of the first particle in the nth mode, the second particle in the nth mode, and all the way to amplitude of particle n in the n normal mode, and cosine of omega nt. Okay, let me write this n better. Nt minus delta n. So constants of integrations, which are determined by the initial conditions, are f's and deltas, constant of integrations. So let me write something about that as well. Okay. Initial conditions need to be used to find f case, delta case can be found using, of course, initial conditions, I sub c, IC. Okay, so that is the general solution of the whole system, of which consists of n particles. But of course, quite often you want to know what's the general solution of particle 1, then general solution of particle 2, and so on, right? So in this case, it's very simple. You just need to grab all the top elements, of course, with time dependencies, right? So this will be your, all right, general solution of particle 1. Of course, cosines must be also included, and so on. So let me write that down. All right, so general solution of the first particle. So now we can write, so general solution of the first particle, only the top elements. So it will be eta 1 equals F1 A11 cosine omega 1 t minus delta 1 plus, okay, let me write the second element also. A 1, 2 cosine omega 2t minus delta 2, and then plus so on, plus, and the last one, so it will be fn a1n, and okay, let me step away slightly further, so cosine omega nt minus delta n. So then the same for eta 2 f1 a 21 cosine omega 1 omega 1t minus delta 1, and so on till the last term fn a now 2n and cosine omega nt minus delta n, and so on. And now let me write in general general solution of a particle k. Right? So now you see the tendency, and now we can write eta k equals, so it will be summation over you know what, k I used, no, actually I used I. Okay, let me use also I, because now I'm started thinking I used k in a different. Okay, so it's not a big deal. Eta I, mode number I. Summation over k from 1 to n, and where this I, so it's over here, right? So it will be f k a I k and cosine of cosine of omega k t and minus delta k. Okay, it looks like correct. Let me check my notes also. aik cosine, yeah. So that's general solution of particle I. Right. So basically, it's a what's the construction of general solution of a certain particle? You take some contribution from the first normal mode, amplitude is given, then some contribution to the motion of the first particle from the second normal mode, then from the third, and so on. So a bunch of contributions from each mode to the motion of that particular particle. So that's what we have. Yeah, small pieces from everyone, right? Right. Okay. So this should be framed, but it's too big, right? So, and of course, I think this should be also framed. General solution of particle number I. Okay. So now, in order to continue, sort of logically, no, not logically, just mathematically, let me rewrite this in the complex form again. Of course, in real life, that's what you need at the end of the day, right? So you need to know the real actual displacements which are real. But let me write it in the complex form. You will understand why in a second, right? So now let's go back. Let's go back to the complex form. Okay, so basically this is the solution, right? So now I'm trying to make prepare and transition to the next step. And so, of course, I can write it as eta I equals, so now, of course, we will bring back ck. Right, so it will be real part of course, eventually summation of k from 1 to n. And I think ck I brought back, right? Yeah. ck aik and e to the power of minus I omega k t.
I can't hear you.
Still muted. I was still muted, sorry. um, whenever I drink or do something right outside of the class, I usually mute myself, but sometimes forget to unmute. Okay, so basically the problem is solved. This is general solution. And so now you remember what in the previous class we showed that using model matrix and congruence transformations, we can diagonalize simultaneously kinetic energy matrix and potential energy matrix, right? Kinetic energy matrix gets transformed to just unit matrix, diagonal elements just one, and potential energy matrix gets transformed to a diagonal matrix and eigenvalues with eigenvalues along a diagonal, right? So what does it mean that a matrix which represents a certain physical quantity, okay, in first case it's kinetic energy, the second case it's a potential energy, right? It's a certain physical quantity, right? So what does it mean that matrix is different? It means that if you go to a different coordinates, of course the matrix will have a different form, right? You go to another set of coordinates, right? So of course the matrix, all the matrices will be transformed. So since we demonstrated that it's possible to diagonalize those matrices, it means that there are a certain set of coordinates where those quantities, okay, matrices of those quantities, where matrices of those quantities have a diagonal form. So now, of course, the logical question, okay, great. We proved that these coordinates exist. Now, of course, logical question, let's try to find them. Which coordinates are those where kinetic energy matrix is unit matrix, potential energy matrix is diagonal matrix with eigenvalues along the diagonal. So now the question about coordinate. And since it makes sense, since model matrix transforms our matrices, it means that most likely the same model matrix is going to transform our coordinates, right? So we're going to move from our etas to somewhere else, okay, to the better world again, right? Where the solution will be easier, right? So now, logical question, let's try to find those coordinates. And of course, I'm talking about normal coordinates, right? Okay, so now new title, normal coordinates. And of course, in order to start from that next section, about the next section, I needed this form, so that's why I sort of digressed a little bit to write solution again back in a complex form. Okay, I don't need all this. All right, I can erase. So what about time? Okay, we still have 15 minutes. Okay, cool. So we will be able to finish it today, and the next class we will start with examples. No, next class is the exam. Sorry. Okay, normal coordinates. And so the logic is, look, look at the solution. Time dependence of these coordinates sort of is this okay? Okay, yeah, or we can say, yeah, time dependence of coordinates depends on what? On frequencies of on depends on all frequencies, all normal mode frequencies. So you see we have here summation over k from 1 to n omega k. So oscillations of this coordinate depends on all frequencies, omega 1, omega 2, omega 3, and so on, the whole spectrum of frequencies. Nothing wrong with that. This is the solution. This is the correct solution, right? So we cannot complain. Actually, we can complain, right? But we cannot say that this is wrong or something is not right with that. No, it's absolutely correct. But every time we're trying to simplify our life, right? Somehow we're trying to be sneaky and find the easiest way, right? So it makes sense to ask a logical question. Is it possible to go from these etas to a new set of coordinates where, for example, let's say coordinates psi, right? So where, for example, psi1, the first coordinate, is going to oscillate only with frequency omega 1, for example, with the frequency of the first normal mode only. The rest of the modes, no contributions from the rest of the modes. Because right now, you remember, we collected contributions from each normal mode. A little bit from the first mode, a little bit from the second mode, right? A little bit from the third mode, and so on. Sort of, yeah, please donate your money, right? Like a tax collector, right, from everyone, right? But now, is it possible to go to a new set of coordinates where psi1 would oscillate, for example, with the frequency omega 1, psi2 would oscillate only with the frequency omega 2, no contribution from omega 1, no contribution from omega 3, and so on, right? And so on. So that's the logic. That's where we go. From this point, we're going to start, right? And let me um, I'm thinking, should I rewrite the solution again one more time? Yeah, let me rewrite it since we are now under new title, and then I will write what I just told you, right? So the major idea, the starting, the point from which we're going to start. So eta I, right? So it's summation over k, ck, a I k, and e to the power of minus I omega k t. Okay, and now let me write, because it's a very important for understanding. So let me write this sentence. I just copy, rewrite it from my notes. So can we choose a new generalized coordinates, new, for example, new generalized coordinate psi i's. I like this letter psi. It looks like a snake, and it's easy to write it and fast. In such a way, new generalized coordinates in such a way that each of them each of those xi's executes only one simple oscillation. Each of them executes only one simple oscillation. okay, maybe I emphasize, so psi1 with omega 1, psi2 with omega 2, and so on. Why not? It doesn't hurt to dream, right? Right. As long as somebody can pay for your dreams, right? That's why we need grants, right? Right. Look, what if actually we will see at the end that what I'm going to suggest is correct. What if we take, for example, this, right? Yeah, and call it psi k. So everything except for, okay, summation and that column of amplitudes, psi k. Again, I'm just dreaming, right? Sleep lecturing, sleep walking, right? Sleep lecturing, right? Dreaming. Right. Okay, so as a result, I can write. So let's try this. Try this. Okay, so as a result, we can say that we can define. So we can say by definition, let's define. So we're going to try that as a result. We can take this as a definition. Right. So as a result, 8I equals, I'm just rewriting this with psi, summation over, okay, summation over k, of course, from 1 to n, a I k psi k. Or we can write it, of course, in a matrix form, right? In a matrix form, this can be written, of course, we'll have column eta equals to model matrix times the column psi. Okay, let me frame it, since we're basically taking this as a definition. Right. Or, yeah, maybe I can frame this in blue because it's a matrix form, right? So now, that's how we can move from what? From xi's to etas. But we have etas, right? So of course now we need to sort of develop a bridge in the opposite direction. So what about the reverse direction? Right, so let's invert it. So let's invert it. Invert it. So in order to invert it, let's multiply left-hand side and right-hand side by, okay, let me write here underneath, by A transposed T. That's A transposed A tilde T. Both sides of the equation, left-hand side and right-hand side. You're not, I guess. It's not illegal so far from the mathematical point of view. So A transposed T eta equals to A transposed T A and psi. Again, psi, probably I should say it. So these eta and psi's, of course, columns, right? Columns. And of course, A is the model matrix. Okay, so now this A transposed TA, it's a congruence transformation of our kinetic energy matrix, which gives us unit matrix. So now it's not just one, it's a unit matrix. And you see this fancy one, right, with two lines, vertical lines. So it's a unit matrix. So as a result, if you multiply, of course, this unit matrix 1 by column psi, you will end up with just psi. Again, psi is the column. So now that's the procedure to go back. You know what? Let me write it here, or maybe I'm thinking about framing it somewhere. Okay, let me write here in the corner. So it will be A transposed T eta, right? And we can frame it. So that's how we can find normal coordinates. Actually, I defined psi, but I didn't write down. I didn't write it down that these are normal coordinates. Okay, let me write down. So, psi i's are normal coordinates. Right. And so if, but of course, logically, usually, like in your life, if you start solving problem, okay, finding the general solution of coupled system, of course, first you go through the regular procedure, find all these etas, and then if you want to go deeper in your analysis or so on, all right, then you need to go from etas to psi's. Of course, you will have to use this, right? Because usually you found eta, and then you can try to find psi's, where life is better, right? Analysis is better, right? Right. Okay, still have 5 minutes. Awesome. Right. So let me check. So we defined that. That is also here. Okay, great. So that's how we can move to these coordinates, normal coordinates. But you know what? We move to these coordinates, but still we cannot guarantee that we are at the right place, that we are at the right coordinates. Right. So let's see what happens to the kinetic energy and potential energy. Are we going to get only quadratic terms and no coupling terms? It means that kinetic energy matrix is a diagonal and potential energy matrix is a diagonal. Yeah, it's cool. We introduced something interesting, right? And we know how to get there. But who guarantees that this is the right place? Who guarantees that your kinetic energy is going to have the simplest possible form and potential energy? So of course we need to show that. Makes sense. So let's see what can we get in these coordinates, right? So now let me write. Okay, I will put a small bullet. So what will happen? Will happen what to V and T. Again, right now I'm not talking about matrices only. I'm talking about kinetic energy, potential energy, right? T and V in terms of size, in terms of size. Okay, question mark, of course, must be position over there. Right. Okay, so now from the definition, the very beginning of this chapter, we wrote down kinetic. Let's start with kinetic. Yeah, let's start with kinetic. So kinetic energy was introduced like this: summation over I think IJ use IK. Okay, why not? IK 1 over 2, then TIK, and eta I dot eta K dot. It's the very, very beginning when we use Taylor expansion, right? Okay, so now we know how to move from etas to psi's. Let's do it, right? And here. So that's what I'm planning to use. So I can write it like this. Okay, 1 over 2 I will take outside. And okay, let me write. So summation over ik, then tik, and then I will introduce summation over alpha from 1 to n. And first I will rewrite eta I dot. So eta I dot, it will be just this, but with dot above. So it will be summation over alpha. So it will be a I alpha psi alpha dot. That's eta I. And now the same, of course, I can write for eta k dot. So it will be summation. Now, of course, instead of alpha, I will introduce beta, right? Because we have two different sums, of course, indices must be different. And now it will, of course, will be a, now it's a k beta, k beta and psi beta dot, and close the second bracket. So it's a k beta and psi beta dot. Okay, so you remember we want to write in terms of psi's kinetic energy. Of course, summation over alpha and beta must be taken outside, and psi alpha and psi beta dot again must be taken outside, and everything what will be left we'll construct inside, and see what can we get out of that. 1 over 2, let me take outside, so summation over alpha and beta, as I said, because those are indices summing psi dots. Right, and inside we have, okay, let me finish at least this kinetic energy. All right, so let me write like this. First, I will write this a k beta, right? Then t I k. These are components. Of course, components you can move, arrange any way you want, right? But of course, when you go to the matrix form, of course, you need to arrange them properly and then only transform to the matrix form, right? And a I alpha, all right? Summation over ik. I forgot to write, and now I'm lazy to rewrite it. No, I have to rewrite. Sorry. So summation over ik, right? So it will be a I alpha t I k and a k beta, and psi alpha dot and psi beta dot, alpha dot and psi beta dot. What is inside of these parentheses? And on purpose, I arrange terms like that. So we have inner indices the same. Here would be the same, but if you transpose the first column, right? So it's a transposed, right? So what we have here, it's a transposed T A, written in a component form, which is a congruence transformation which diagonalizes our kinetic energy matrix, which gives us a unit matrix. Okay, but of course, it's a component form. Of course, in a component form, that's what I need to write it over here, right? So in a component form, of course, it is equal to delta alpha beta, right? This is a unit matrix written in a component form, delta alpha beta, right? Which is great because this symbol Kronecker is going to kill one of our sums. Right now we have two sums. Who wants to deal with two sums, right? It's better to slaughter one of them, right? So as a result, we will end up with 1 over 2 summation. Okay, I will get rid of beta, of course. So it will be just a alpha, summation over alpha. And here, again, beta will disappear. We'll have psi alpha dot squared, quadratic terms only, no diagonal terms, right? Psi alpha dot squared, right? Okay, so that's, and of course I'm supposed to put a big happy smile because no diagonal terms, only quadratic terms. Only quadratic terms. No diagonal terms, pretty much no coupling terms. No diagonal terms, no coupling terms. And those coupling terms in the kinetic energy are called dynamic coupling terms. Of course, it's not a big deal. But of course, it makes sense why they're called dynamic, because kinetic energy is energy of motion, right? No coupling terms. No coupling terms called dynamic coupling terms, called dynamic coupling. Oops. Right. Okay, basically, yeah. And of course, if you write matrix, yeah, it will be diagonal, right? And actually, we used it, right? So yes, this is at least 50%. So we convinced ourselves, yeah, that this is the correct coordinates where kinetic energy matrix has a diagonal form. But of course, we show theoretically that at the same time, the same matrix is going to diagonalize potential energy, right? So at this point, I can say, I can bet all my money that even potential energy is going to have a quadratic terms only, no coupling terms, right? But of course, we will prove it anyway next time. So pretty much a little bit left. So like what's left, we just need to show that potential energy will have coupling terms only, right? Then we will write Lagrangian in terms of these new normal coordinates. And of course, Lagrangian is going to be decoupled completely, right? And as a result, the system will be, not the system, Lagrange equations are going to be completely decoupled. So equation number 1 is going to give you, will depend only on psi1. The second equation will depend only on psi2, which can be easily solved. It's a undergraduate level solution, right? So we're going to have just n simple harmonic oscillators, right? Basically in these normal coordinates. Right. And you know what, before we go, I want to emphasize, right? So up to this point, ATAs, they define position of actual position of particles, okay, measured from the equilibrium points. Once you move to psis, no one is going to guarantee that these psis are going to define positions of particles. They can define any points in the system, right? For example, right, so that you wouldn't panic at this after these words, you remember central force problems. We moved from R1 small and R2 small to where? To R capital. What R capital defines? Position of the center of mass. What is center of mass? It's just some fictitious point in the system, right? So we've seen something like this, right? So the same here, right? So psis can define any points in the system, right? But ATAs, yeah, they define positions of particles relative to the equilibrium points. Okay, so pretty much that's what left, and after that we will start looking at a couple of examples. First, kind of example, more or less realistic, typical example, and then the next one will be weakly coupled system. For example, we have two oscillators, right? But coupling between them is very weak. We will see some interesting phenomena, right? Like transferring energy between two parts of the system, right? So that's what we're going to discuss, okay, not next class, next week.